Greetings. So, we are at this very exciting phase of understanding what is this Feynman path integral approach, and it is a beautiful approach. It is not making use of the wave particle duality, it is not making use of the fundamental uncertainty principle, the commutator Q comma P is not what we have used, but we get it in terms of this integration, this multiple integration, in fact over infinite paths. So, the Feynman particle can go anywhere in the universe between its start to the finish. And as we discussed in one of our earlier classes, Feynman quantum mechanics actually requires you to consider all of these paths, because the summation is over all the histories, all possibilities. It might take the particle to Mars and back in between, but you are required to consider that. Anything that is possible has to be considered as something that can actually happen, right? The probabilities may be low. And why are the probabilities low for non-classical paths in most of the situations? It is because the variations in the neighborhood of what turns out to be the classical path, they cancel each other. Whereas alternative paths in the neighborhood of what turns out to be the classical path, they reinforce each other, okay? Because they give you the same result to order, if you ignore the quadratic perturbations, terms in powers of 2 of the perturbation parameter epsilon, whereas the non-classical paths give you a correction in the first order of epsilon, which you do not want to dismiss, and those are the ones which will cancel each other because of the oscillatory terms in cosine and sine, okay. So, classical mechanics results when the action is much larger than the Planck's constant, but it is the same action which is defined in the Hamilton's principle of variation. So, this is not defined differently. It is the integral L dt, where L is t minus v, okay. So, this is the Feynman path, and now there are infinite paths. Each path contributes some constant times e to the I theta, right, and whether the e to the I thetas of all they superpose constructively or destructively is what will determine the resulting probability, and the action is obtained exactly the same way as we did in classical mechanics, but the interference, the quantum interference from alternative possibilities is resulting from this phase, okay, because the probability is then given by the square of the amplitude or the amplitude multiplied by its complex conjugate, right. So, that is how you get the modular square, and it is this which leads to quantum phenomena. And the classic example is of course the Young's double slit experiment. Those of you who have watched Feynman's lectures on the YouTube, you are familiar with this, that Feynman emphasizes the fact that all of the essence of quantum mechanics is in the understanding of the Young's double slit experiment, okay. There isn't much in quantum mechanics which is not there in the analysis of the Young's double slit experiment. So, this is a wonderful experiment to work with, and we are now going to ask, does Feynman path integral provide you an understanding of the Young's double slit experiment? Does it explain the interference pattern? Does it give you the dark and the bright fringes? We know we get it from light waves from Young's analysis, which sort of established that light is a wave, right. and then we can do it with particles, and then we can do it with light as particles described by waves, okay, and exploit the wave particle duality. Feynman talks only about particles, whether it is light or electrons. There are only these Feynman particles. Okay? And you have got a source of Feynman particles. It can be light, it can be electrons, it can be anything else with which you are conducting the experiment. And this is an experiment with Feynman particles, and we know from our previous experience of the Young's double slit experiment what the result is. You expect interference fringes patterns, and the question in the early days of quantum mechanics is, okay, what is it? Is it a wave or is it a particle? And then on Mondays, Wednesdays, Fridays it is a particle, on Tuesdays, Thursdays and Saturdays it is the other thing, and then on Sundays you just sit down and pray, let me know God, what is it, alright. So the question is not, the right question is not what is it a wave or is it a particle, is not the right question. And this is what Bohr tells us, that you don't get answers to all the questions, you learn what is the right question to be asked. The right question to be asked is not whether an electron is a wave or a particle. The right question to ask is, how do you describe the electron correctly? What is the correct description of nature? That is not the same thing as asking, is an electron a wave or a particle? These are two different questions. And nature nature is nature, whatever it is. And physics describes it correctly. That the correct way of describing the electron is that you represent it by a state vector in the Hilbert space, its evolution being given by the Schrodinger equation, that is one way of doing it, or dynamical variables by operators which satisfy a certain algebra, which is quantum mechanics, or the probability amplitudes are given by the Feynman propagators and you describe it, right? And that is the law of nature, it gives you a correct description of nature. So that is the right question to be asked. And you can call it as anything, and we considered calling it as a golf cun or golf ball or something like that, that you actually need a new term, and you can call it as anything, but what you are attempting is you are trying to describe what it is. It is the description which has to be self-consistent. So that is quantum mechanics, and quantum mechanics provides you the correct description. So here is the interference experiment, and here is the Feynman law. Okay? And we are going to ask, how does the Feynman law account for the fringes you see in Young's double slit experiment? Because this, we know, is one of the most fundamental things in quantum mechanics. So you have got this probability amplitude for the Feynman particle, which is given by an amplitude times e to the I theta. Okay, theta is the phase that you get from the ratio of the classical action to the quantum action. Okay, and the probability itself is you sum over all of these amplitudes and then take the square of that. That is the net probability. So we have to determine this Feynman probability amplitudes, add them up and then take its square. So how is the particle getting to the detector at the point D, let us say? It goes from the source, which is the point A in this figure, it goes to slit 1, S1 and then to D. Alternatively, it can go from A to S2 and then to D, right? It can get scattered by something in between and go to Mars and make a round trip and get back. Okay, we have seen those possibilities earlier, right? In our first first or second lecture in this series of lectures on path integrals, we considered some stoppers in between which whirled it into space, right, and it got back, be it so, okay. And then the probability is going to be determined by taking the square of all the summation of these different probability amplitudes. And each path you segment into the steps. It goes from point A to B and from B to C, or it can go from A to some other point and then to this point, right. So, we have two alternatives in the Young's double slit experiment to consider. One is slit S1, the other is slit S2, right. So, there is some intermediate point. This is what I call as a waypoint, intermediate waypoint. On your way, you go via, on your way to school, you go via a restaurant, have a cup of coffee, or go to some other restaurant and have a coffee, right. So, these are the alternative paths that you are going to consider. One is via S1 and the other is via S2, and the Feynman particle could go from A to S1 and then from S1 to D, or A to S2 and then from S2 to D. In between, it functions, its travel is described by that of a free particle, which is also Fp. Okay. So, a free particle is Fp, a Feynman particle is Fp, and this probability amplitude must be added from A to S1 and S1 to D, and then from A to S2 and S2 to D. So, you add up these two probability amplitudes, okay. This sum is what gives you the left hand side, and the probability and the interference pattern is going to be generated by the modulus square. So, is this expression simple, right? So, this is what you have to determine. Each amplitude will be given by a certain constant times e to the I theta, and here is the fun part, because in between it travels as a free particle that we know, right. It is going via the waypoints S1 and S2, but now look at the symmetry in the figure. A to S1 is completely symmetric, completely equivalent to A to S2. So, though both those probability amplitudes, you can consider them to be equal to each other, and we will represent that probability amplitude as K0. Okay. So, from here you extract K0 as a common factor, and now you have got these two probability amplitudes. What are these probability amplitudes? From S1 to D, from this slit 1 to D, and the other is from slit S2 to D, from here to this point. Okay. So, these are the two probability amplitudes which are going to add up before you take the modulus square. Okay, good. Now, each probability amplitude is given by a constant times e to the I theta. Now, notice that the time the particle would take to get to the point S2 is the same as it will take to get to the point S1 starting from A. AS1 to AS2 time intervals are exactly equal, there is no difference. And the interference takes place because the particle arrives there together from both the paths, right, which means that those times are also equal, which means that the time taken from S1 to D is the same as the time taken from S2 to D. Now, the distance is not the same. One can be 2 centimeters and the other can be a billion light years, because in between it can go somewhere and come back. All right. The particle takes exactly the same time to reach the point D, no matter what its path is. Okay? The distances are obviously different. Okay? And this is part of the reason Feynman says that I think I can safely say that nobody understands quantum mechanics. But if you get this idea, we can move on. Can we? See, the time it takes to go from the source A to the point S1 is exactly the same as it takes to get to the point S2. No problem there, right? The particles reach the detector and there will be an interference pattern. So, they have to be there at the same time, at the same instant of time. So, the time, therefore, the time taken from S1 to D is the same as the time taken from S2 to D, no matter what the difference in this space interval is. And that difference can be a few millimeters or a few billion light years. Okay? Why does this happen is not the question we have to ask. We have to ask, what is the law of nature and how do you describe it correctly? So, if you start asking the question, what is the speed of the particle in between? If they are reaching there at the same time, but the distances are different, then what are the speeds? Is the speed of one path larger than that of the other, that it can travel the larger distance in the same time, including a distance which is large enough to go to Mars and get back? Okay? You don't ask this question. It is like asking, is the moon there if nobody is looking at it? Okay? This was Einstein's objection to quantum theory. Okay? If you don't measure the velocity of that particle, what is its velocity? So, I am not looking at the moon, but I want to know if it is there. So, Bohr told him that no, you have to look at it, and if you look at it, the system will collapse into an eigenstate. So, if you measure the velocity of the particle, the system will collapse into a velocity eigenstate and it will no longer be in a position eigenstate, and then you will not even be able to talk about the particle be on that track, because for the particle to be on a particular track, you need to know its position. But if you measure the velocity, you have lost information about position. So, it will collapse into a velocity eigenstate, into a momentum eigenstate, which will be described as a superposition of an infinite number of position eigenstates. So, the particle will be all over and not just on one track. So, there is no discrepancy here. Quantum mechanics is telling you what is the right question to be asked, because if you know the position, you lose information about the velocity and momentum and vice versa. Okay? So, the idea of a path that we are using in path integrals is different from the path that we talk about in the classical sense. Okay? So, here is what we are getting, that these time intervals from S1 to D is exactly the same as the time interval from the slit S2 to D. The distances are not the same, does not matter, no worries about it. And now each probability amplitude is given by a certain constant times e to the I theta, but in one case it is theta 1, in the other case it is theta 2, because these are two different paths. Okay? So, you have got k0 n times the sum of e to the I theta 1 plus e to the I theta 2, and the probability will be given by the modulus square, or which is k star k. So, you can factor out k0 n as a common factor, take its square, that will give you I, right, and then what you need is the modulus square, or which is k star. What is k? K has got this k0 n, and then you have this e to the I theta 1 plus e to the I theta 2. You have to multiply it by k star, which is e to the minus I theta 1 times plus e to the minus I theta 2. So, you multiply term by term, what do you get? E to the I theta 1 multiplied by e to the minus I theta 1, then you get e to the I theta 1 multiplied by e to the minus I theta 2. So, you will get terms in theta 1 minus theta 2. Okay? And if you write this theta 1 minus theta 2 as xi, then this sum adds up to 2i 1 plus cosine xi, where xi is the difference angle, theta 1 minus theta 2. Okay? So, this probability goes as 2i 1 plus cosine xi, and cosine xi can go from minus 1 to plus 1. So, when cosine xi is minus 1, the probability is 0. When the cosine xi is plus 1, the probability is 4 times I. So, the probability is going to change from 0 to 4i, okay, and it will generate the interference pattern. We have not used a wave anywhere, we have not used the wave particle duality anywhere, we have not used the wave superposition, whether it is the Young's double slit experiment with water waves or with light waves. We have used superposition of the Feynman probability amplitudes of the Feynman particles, and we get the interference pattern. Okay, so let us analyze this result further. So, you have this phase angle xi, it is actually theta 1 minus theta 2, but what you are getting is cosine xi. So, it does not matter whether it is theta 1 minus theta 2 or theta 2 minus theta 1, okay, because cos theta and cos minus theta are the same. So, it does not depend on which is slit 1 and which is slit 2. So, it does not depend on this arbitrary nomenclature. Okay, so, it goes nicely as cosine xi. Xi is just the difference between the two angles, whether it is theta 1 minus theta 2 or theta 2 minus theta 1 does not matter. So, I write it as a modulus of theta 1 minus theta 2. You get the interference pattern because of this, okay. And when xi is equal to 0, 2 pi, 4 pi, etc., you will get constructive interference. When it is an odd multiple of pi, you will get destructive interference, right. And we have agreed, although it may have been with some reluctance, that the time taken from S1 to D is exactly the same as the time taken from S2 to D. Okay. So, this is a quantum idea that we have to bite, okay, and digest it and make it a part of our intuition. Okay. So, the time intervals S1 to D and S2 to D are exactly the same, which I represent as tau. I am aware that the two distances are not the same, and it does not matter in this analysis. The nomenclature 1 and 2 does not matter, okay. And we have the two phases now. One is e to the I theta 1, and what is e to the I theta 1 from the Feynman propagator? It is, if you see this term, it is nothing but x prime minus x0 is the difference length square, which is r1 for theta 1 and r2 for theta 2. The t prime minus t0 in both cases is tau. It is the same time interval, these are equals no matter what the distances are, okay? And these are the two phases now. So, the e to the I xi is given by this ratio, and in the numerator you have r1 plus r2, which is twice the average distance r, and r1 minus r2 is their difference. That difference is what you will call as a path difference in the conventional Young's double slit experiment of optics. Okay? So, delta is the path difference r1 minus r2, and if you now invoke the de Broglie hypothesis that each particle is represented by a wave with wavelength lambda, which is h over p, then you can interpret this. If you look at this expression for xi, you see that 2 cancels. R over tau is like the average speed, okay? M times average speed is like the classical momentum mu, which is coming here, and then you have mu delta over h cross, right? Tau has already gone into u. So, you have mu delta over h cross, and this is the momentum over h cross, okay, times delta. And now you can recognize that the path difference is like the de Broglie wavelength. And you can think of this interference as coming in terms of the de Broglie path difference being either an integral or half integral multiple of the de Broglie wavelength. Okay? So, the first maximum will come when this angle is 2 pi and you get a complete correspondence between the wave particle duality and the Feynman approach, right. So, the de Broglie and the Feynman approach both correspond to each other. That correspondence is brought in by inserting this de Broglie wavelength. Got it? So, this is really not surprising in some sense if the Feynman path integral corresponds to quantum mechanics, which we have already seen, but we see how it accounts for the interference pattern completely satisfactorily and completely in accordance with wave mechanics or the superposition of waves in the optics experiment or the Young's double slit experiment with water waves. Okay? It is rated as one of the most beautiful experiments in physics. If you do a Google search and ask for which are the most beautiful experiments in physics, the Young's double slit experiment will pop up in the top 10 or 20 or maybe even less. Okay? And this is part of the reason. It is at the heart of physics. Okay? It is at the heart of quantum mechanics. It is at the heart of the wave particle duality. It was the one which inspired the debate between light being wave or particles. Okay? And you get a correct description and a correct correspondence. So, nature is whatever it is. Okay? And laws of nature are what they are. And we are not answering why are the laws of nature what they are, but we are answering what the laws of nature are at all. What are the laws of nature? How do you describe these laws of nature? And the answer is that you describe the laws of nature using a certain ansatz using a certain model. So, you develop the machinery to provide a description of the nature and how it evolves with time, and it is in terms of wave particle duality, which is described by a wave function which satisfies the Schrodinger equation, or by Feynman path integrals, and that is what gives you the correct description of what are the laws of nature and how does nature, a natural system, a physical system, evolve with time. So, there are a few comments I would like to make over here, which are somewhat advanced topics which I will not get into the details. The tree here is the place where C.V. Raman was cremated at the Raman Research Institute, and these are scientists from the Raman Research Institute who have considered the Young's triple slit experiment. Okay. And then they show these loopy paths. Okay. And these have been discussed in terms of the Feynman path integral approach, which I will not be discussing, but these come due to some phenomenology which you have some familiarity with, like if you have a step potential barrier which is shown by this red step, and you have got a particle which is incident on it with a kinetic energy which is slightly lower than the height of the barrier, then you know that there is you can apply the boundary conditions, get the reflection and the transmission coefficients and so on. You actually end up getting total reflection, and what you have is an evanescent wave, and this idea is used in the understanding of the triple slit experiment, but I will not discuss it. Those of you who are interested may please study this further. And then of course you can ask the question as to what happens if you cut the step and then there is a possibility of a zero potential on the other side, and if you diminish the width of the barrier, then the particle has the probability of tunneling through, okay, which is a well-known quantum phenomenon. So, all of these things happen in nature, and this idea of the evanescent wave is of importance in understanding the Young's triple slit experiment. There are other similar phenomena which need to be understood. You can have this total internal reflection depending on how the incident wave, at what angle it meets the interface. But then you also have the frustrated total internal reflection, and all of these are very interesting phenomena which one can consider. But this looping in the triple slit experiment has actually been seen and reported in this paper in Nature Communications. This is a paper in, I should have the reference somewhere. Yes, here it is December 2016. Okay, so you might want to go through this who want to read ahead, but I am not getting into those things, and I will stop here for this class with the conclusion that we have a comfortable correspondence between the de Broglie waves, not the de Broglie waves as such, but the conclusions from the de Broglie waves. What is the conclusion? That you have an interference pattern, that light waves arrive either in phase or out of phase, and depending on how they arrive, but this is the phase of the wave, this is the de Broglie wave, okay. Whereas in the Feynman path integral approach, you also have a phase which is e to the I theta, but this is the phase which is coming, which has nothing to do with a wave. It is coming from the e to the I theta factor in the Feynman path integral propagator. Thank you. Questions? Yes.
What if we created a time delay of particle which is like if we done this experiment with two particles from the source, we created a time delay between those two particles. For example, I send the particle
See,
first
the
through S2 and then through S1.
Young's double slit experiment, the most interesting part of this, and this is what which I mentioned um, in one of the previous classes not too long ago. Even with a single photon in the experiment in the whole apparatus at a time, you get this interference pattern. So, you are talking about a single particle, you are talking about the interference of particle with itself because of the alternative paths it can take. It is not between particle A and particle B, and you insert a time delay in particle B. Even with a single photon, you see this interference pattern. You reduce the intensity of the source so that you have got a certain number of particles per unit time, and you conduct that experiment in between the interval between the release of one particle and the release of the next particle. There is a certain time interval. In between, there can be only one particle in the apparatus. And if you let the results accumulate over a period of time, and there are some very beautiful experiments which have been carried out. And I think one or two references I may have included, but otherwise they are not hard to find in literature. And people have conducted these challenging and very beautiful experiments and found that yes, nature requires for its description a quantum theory. Classical theory does not account for it. Okay, thank you.